just finished chapter 8, which was about quantum mechanics, and we learned a little bit about the strange behavior of electrons and about things called orbitals. So electrons in atoms exist within orbitals, and those are like regions of space in which an electron is likely to be found. A description of where the electrons are, which orbitals are occupied, is called an electron configuration. For hydrogen, it's pretty simple because hydrogen only has one electron. So that one electron is going to be in the first principal energy level in the sublevel S, and there's one electron in there. So the large number here is the principal energy level, the principal quantum number. S, P, D, or F tells us what type of orbitals these are. That's the sublevel. And then the exponent tells us how many electrons are in that sublevel. So we also talked about Schrodinger's equation, and doing calculations with that show that hydrogen's one electron occupies the lowest energy orbital in the atom. And this is typical. With the electron in hydrogen, these things can be solved and predicted well. But when you get to more than one electron, which is like everything but hydrogen, right? You cannot exactly solve the Schrodinger equation anymore because you have to add terms that account for interactions between the electrons. So we only get approximate solutions, but those approximate solutions show the orbitals to be very similar to what was calculated for the hydrogen atom. So there are two additional concepts that make the multi-electron atoms more complicated. These are electron spin and energy splitting of sublevels. Another way to indicate where the electrons are is using an orbital diagram. So here we use a box to represent each orbital, and we use a half arrow to represent each electron. So for hydrogen, this is the 1s orbital. There's one electron in it. We talked about spin and the spin quantum number, plus 1/2 or minus 1/2. So by convention, we fill these first with a plus 1/2, which would be pointing up, and then another one would be down pointing arrow, which would be minus 1/2. So if you look at a group of hydrogen atoms, they each just have one electron. About half of the electrons are spin up and about half are spin down. So, we can write this with spin up, but that doesn't mean that all hydrogen atoms have one spin up electron. We talked about 4 different quantum numbers. And it turns out that each electron in an atom has its own unique combination of those 4 quantum numbers. So it's a bit like a social security number. No one else has the same social security number that you have that identifies who you are. It's unique for each person. So the Pauli exclusion principle is what this is called. It says no 2 electrons in an atom may have the same 4 quantum numbers. Now, if we have 2 electrons in the same orbital, 3 of those numbers are going to be the same. They're going to have the same principal quantum number and the angular momentum and the spin magnetic. So then the last one has to be different. So we understand this to mean that each orbital can have a maximum of 2 electrons, and they must have opposing spins. One will be spin up and one will be spin down. Any questions about that? You could also think of it a bit like an address, right? So, 2 people living on the same block. Well, they live in the same country. They live in the same state. They live in the same city. They even live on the same street. But their house numbers are different, right? This is all very nice. If you know the number of orbitals in a sublevel. You can figure out how many electrons could be in a sublevel. I really just don't find that very useful. So helium. Helium has 2 electrons. So the electron configuration for helium is 1s2. So now there's 2 electrons in this 1s orbital. The orbital diagram, here's the 1s orbital box, and now we see that there are 2 arrows in there, one up and one down. If we look at the quantum numbers for these 2 electrons, they're both in principal quantum number 1. L is 0, m sub L is 0 for both of them. So far everything's the same, but then the last one is going to be different. One's plus 1/2, one's minus 1/2. So this combination of 4 numbers is specific to this one electron. Each electron in an atom is going to have its own combination of quantum numbers. In hydrogen, when we look at the sublevels, that would be like S, P, and D, and F. If we look at the sublevels of each principal energy level, they are all the same energy. The energy depends only on the principal quantum number. Degenerate is what a word we use to refer to that. So those degenerate orbitals have the same energy as each other. When we get into electrons, when we get into atoms with more than one electron now, the energies of the sublevels get split. They are no longer degenerate. They're no longer the same energy. And this splitting is caused by charge interactions and by shielding and penetration. In general, we can say that the lower value of L in a principal level, the lower the energy of the orbital. So again, S is L equals 0, L equals 1, L equals 2, L equals 3. So in a given level, the S sublevel is going to be lower in energy than the P. Any questions yet? Or maybe I went past the point of questions. Did I already get past that? I hope not. We're getting to the hotel. We're going to get to the hotel today. Okay, so Coulomb's law relates the energy of 2 charged particles. And this is not an equation that we need to remember. What's important here is not being able to calculate the energy of charged particles, but in understanding how the energy changes with respect to the radius, the distance between the particles and their charges. So this energy is equal to the charge of one times the charge of the other. So if we're talking about attracted energy, we have one that's positive and one that's negative. So Q1 times Q2 is going to be a negative number. And that means that the charges are attracting. If we have 2 like charges, 2 positives or 2 negatives, then E will be positive, and that means the electrons repel the charges repel each other. So the energy depends on the size of the charge, the magnitudes of the charges, and it also depends on the distance between them. The further apart they are, the less attractive force there is, or repulsive force. So potential energy increases as they get closer together, and potential energy increases when the size of the charges increases. Does that make sense? Or do you want the magnet on the refrigerator analogy? Magnet on the refrigerator? Okay. Electrical charges and electrical fields are a little hard to get your mind around because we don't actively deal with them in real life, right? But magnetic fields are very similar, and everybody kind of likes magnets, right? There's magical, right? You stick it on a metal surface, and it just sticks there. No glue, nothing. But then you put it on another kind of metal, and it doesn't stick at all, and what's up with that? Not all metals interact with magnets. Anyway, you can put a magnet on your refrigerator door, and it'll stay there, right? And you can stick a piece of paper, maybe you've got a notice about upcoming dental appointment. So you stick it on the fridge and you put it up there with a magnet. It stays up there just fine. But what happens as you continue to add more and more pieces of paper under that magnet? At some point, the magnet will still stay there, but now the whole thing starts to slide down, right? And you get too many pieces of paper and it won't stick at all. What's the difference? Well, each piece of paper increases the separation between the magnet and the refrigerator. So as R gets larger, the attractive force between the magnet and the refrigerator gets smaller. Then there are also different strengths of magnets. The people in my house love taking apart computers and getting the magnets out of the hard drives. And they're really, really strong magnets, right? Much nicer than the souvenir fridge magnets you get at some, gas station, right? So we have a gas station fridge magnet, and then we have one of these super duper ones from a hard drive. The really strong magnet can hold up a lot more paper, right? Because this Q1, Q2 term is much bigger. The magnetic field is stronger. It also takes a lot more force to pull it off, right? And there's my friend, the train. We should keep track of when they come. So that was 6:23, if you're paying attention. In fact, some of those really strong neodymium magnets, you almost can't pull them apart, okay? So if the charges on these electrically charged particles are larger, that's like the stronger magnets. They're going to stick together stronger. And then the distance will still affect them, right? Even a super strong magnet, you put enough pieces of paper, separate it from the refrigerator enough, and it's not going to stick anymore. Does that make sense? So each electron in a multi-electron atom has attraction to the nucleus and repulsion from the other electrons. Because electrons all have negative charges, and two negative charges will repel each other. The nucleus is positive in charge and has an attractive force for the electrons. The repulsions from the other electrons cause the electron to have a lower attraction to the nucleus. And so we say that it's being shielded from the attractiveness of the nucleus. If we look at the total amount of attraction that an electron feels for the nucleus, we can call that the effective nuclear charge of the electron. What?
It's a drama from 1B, sorry.
Oh, I thought you were anticipating the analogy that's coming up about that.
No.
So then the closer that an electron gets to the nucleus, the more attraction it feels, right? Because there's that distance term in Coulomb's law. So if you have an electron that is good at coming into, we say penetrating the cloud of another electron and getting in close, kind of sneaking ahead in line or budging in, it's going to have more attraction for the nucleus. So the degree of that penetration relates to the orbital's radial distribution function, which we kind of briefly talked about last week. Okay, let's look at this in an example. So here we have a lithium atom, 3 positive charges in the nucleus, and we've got 3 electrons. So these 2 electrons are in the first energy level. They're in that 1s orbital, which is spherical, right? And so they're bopping around. They're mostly going to stay in this volume. This electron is in the next energy level, so it's a little bit further away. When this electron looks at the nucleus, these other 2 electrons are kind of in its way. Because they're not just sitting here and sitting there, right? And they're not going around in circles. They are like a standing wave, and they are like in the whole thing, right? And so as this looks through that cloud that they make, it can't see the nucleus as well, okay? So the nucleus here is like a bodybuilder at the beach, okay? And the shielding idea here is it's cold, and so the bodybuilder is wearing a parka, right? And so you look at him and, like nice, calves and stuff sticking out the bottom, but I can't really see how attractive this person is, right? So they're being shielded by the clothing, right? So if we have an electron whose orbital allows it to get in closer, this is like going in there and opening up the parka, right? And now we can see, and then the person's more attractive, right? Because you can see how beautiful their body is. How's that for a weird analogy? The weirder, the better. So when this electron looks at the nucleus, it sees this charge, +3, and we have to subtract off these other 2 electrons that are kind of getting in the way. Whereas this guy that can come in to this same space now sees the full +3 charge. And so that electron is going to be more attracted to the nucleus than this guy out here. Okay? So here's where those radial distributions come in. So the 1s orbital is a sphere, and this is way off the chart here, but it's in really close to the nucleus, right? It's really fading out at about 100 picometers from the nucleus. And then in the second level, we have s orbitals and p orbitals. And the s orbitals have a node in them. And so there's a node here, and so we've got this little bump that gets in here, which is deep down inside the 1s orbital. Although most of that orbital is larger and outside. But a little bit of it can penetrate into the space occupied by the 1s orbital. And so now I can see the full glory of the charge on the nucleus. The 2p orbital is roughly the same size as the s, but because it doesn't have a node, it doesn't penetrate in very much. And so that makes the 2p orbital a little higher in energy than the 2s orbital, because the electrons in the 2p orbital can't get quite as close because they're not penetrating very well, and they've got more shielding from those 1s electrons. So this is explaining why there is splitting of sublevels. It's great if you understand that. It's okay if you don't. If you just, believe me, it's fine. So because of that, the sublevels in each of the principal energy level are not degenerate, they're split. And this gets more and more important as you get up into the 4th and 5th principal energy levels. Now those effects become so important that the 4s orbital is actually lower in energy than the 3d orbitals. And so the order of these gets all wonky. We also see that the energy separations between one set of orbitals and the next become smaller and smaller once we get past 4s. In fact, the relative energy ordering can vary among elements, and we're just going to be talking about kind of the most common ordering. So this is a general ordering of orbitals for multi-electron atoms. So here we see this is the first principal energy level, the second, the third, the fourth, and a little bit of the fifth. So the first level, that sublevel, all less energy than the second level. And the second level is all lower in energy than the third level, although now we've got S is lower than P. Here S is lower than P, and then D is higher. But because of the penetration of the 4s orbital being able to get into the space of the 1s and 2s electron orbitals, this is actually lower in energy than the 3D sublevels. And then there's 4p, and then 5s sneaks in here, and then there's 4d. And so this leads to what seems like a kind of crazy ordering of all these things. 1s, 2s, 2p, 3s, 3p, 4s, 3p, 3d. yeah, it gets complicated, right? So this is the filling order, but we don't need to memorize that because I'm going to show you how we can see this on the periodic table. It's all hiding in plain sight. Electrons are going to occupy orbitals with the lowest energy because that's what nature prefers, everything going to the lowest energy. Balls roll down hills, they don't spontaneously roll up. In a given sublevel, like 2p is a sublevel, there are 3 orbitals in that sublevel. Those orbitals are degenerate. But the sublevel, 2p and 2s, those are not degenerate. The 2p is higher in energy. So we already learned about the Pauli exclusion principle, that the orbitals can hold no more than 2 electrons each, and the spins of those electrons are opposite. Now, is anybody wondering, well, if electrons repel each other, how can you have 2 electrons in the same orbital? That doesn't seem like it should work, right? They're both negative charges, don't they repel each other? Well, it's kind of mysterious, but the spin business, if you have opposite spins, those electrons can get along. We say they're paired, and they can get along and coexist in the same orbital. We're not going to go into that because I actually don't think I could explain any more than that. I'm okay with it, right? So it's the different spin that allows 2 electrons to occupy the same orbital. And then there's another rule called Hund's rule. That means that when we're filling degenerate orbitals, the electrons will fill them singly first with parallel spins. And we're going to go over this in the analogy. Okay. So, the Quantum Hotel, a discount resort for electrons in Mrs. Cave's chemistry land. So, what I'm thinking about there is that this looks like a diagram of a hotel. Now, granted, a pretty weird hotel. This might be like in Las Vegas or something. You know, they have a pyramid hotel. This one's kind of like half of an inverted pyramid, right? So, let's see. I have to draw down here. So, you know, these might be the walls, right? And it goes up as you get out. You don't want to have this built near a fault line, right? Earthquake territory, not good. So this is the first floor of the hotel, and there's 1 room on the first floor. That corresponds to principal quantum number 1. On the second floor, there are 2 rooms. On the third floor, there are 3 rooms. On the fourth floor, there are 4 rooms. We don't show the other one, but it would be the F room, okay? So you could think of these as being the rooms. And, you know, you've got really creative names, 1S, 2S, 3P, etc. So those are the rooms. The lines here, each line represents an orbital, and the orbitals are beds in the room. So each floor has an S room. This is the elevator over here, the energy thing. Each of the S rooms has just a single bed in it. Each of the P rooms has 3 beds, a little odd. The D rooms have 5 beds. Now things are getting strange. And the F rooms have 7 beds. Weird, right? It's electrons. Everything has to be weird. Okay? So that's what we're saying here. The first floor has 1 room, the second floor has 2, the third has 3, third floor 3 rooms, right? The S room has 1 bed, P rooms have 3, D have 5, F have 7. How do you remember that? Counting by 2 odd numbers. 1, 3, 5, 7. Okay. It comes from the combination values of L and M sub L, but we don't want to think about that, do we? No, we don't want to do that. And another rule in this hotel, which corresponds to Pauli's exclusion principle, is you can only have 2 people in a bed. The people are the electrons. And they have to have opposite spins. So we're not talking about gender here at all, okay? Electrons don't have gender, there's just one kind, right? But this, I think where I got this idea from was visiting Fort Snelling in Minnesota, which is a very old fort, and gets really, really cold in Minnesota. And they had this fort, back in the 1800s, right? And they didn't have central heating or anything, and it was 40 degrees below zero absolute temperature. And how do people stay warm, right? So the bunks that they had for the soldiers were very narrow. They were even more narrow than a regular twin mattress. And you're like, what the heck? These guys slept warm because they slept together. And to fit in that narrow space, they would sleep head to toe. So one guy is sleeping with his head at the top of the bunk, and the other guy is sleeping with his head at the bottom of the bunk. And that allows the bodies to fit closer together. Okay? So with the electrons in the bed, one of them is going to sleep right side up in the bed, and the other's going to sleep upside down. Now, of course, this has modern air conditioning and heating and everything, so they're not doing this to stay warm. They're just doing it because it was kind of icky to sleep in the same bed with a stranger, right? So they're going to sleep upside down and just like, we're not doing anything here, right? So the correlations here, the floors in the hotel are the principal shells or levels. The rooms are the subshells or sublevels. Each bed is an orbital. A person is an electron, and money is energy. So as you go up the floors in the hotel, the price to stay in that room becomes higher. And this is a discount resort, right? Electrons here are trying to save money, and so they want to stay in the cheapest room possible. Any questions yet? Oh, I didn't need to go back because here's the slide I was drawing on before. So we could think of as, big bus of electrons comes in and wants rooms. And the first electron, that comes up to the front desk, he wants the cheapest room possible. And so he's going to get this bed. Whoops. The next electron comes in, and he's not real keen on sharing a bed with this guy he doesn't know, this person he doesn't know, but cheapness wins out, and so this electron's going to sleep upside down. So the next electron comes in, and the cheapest room is taken, so he takes the next cheapest room. Next electron comes in, well, I'll share a bed with that guy. Now, this room, there's 3 beds. So you have to pay to sleep in this room, right? So the first guy takes the bed closest to the door because they're tired, right? Come in and just crash. Where's the second person going to go? Is the second person going to curl up with this one that they don't know? No, they're going to take their own, right? That's the Hund's rule. When we're filling orbitals that have the same energy, they'll fill them singly first with parallel spins. All these guys are choosing to sleep right side up because that's what humans do, right? That's what electrons do. They want to sleep the regular way. It's only when you have to share this with another electron that you sleep upside down. So where's the third electron going to go? It's going to go over here and sleep right side up. Now we have another electron. Well, they're too cheap to pay for another room. It's more expensive, so they're going to come in here and they're going to go upside down, and these guys are going to have to pair up. And this is order of filling, right? And so here's the next one, and the next one's going to pair up. You like this? This is my favorite. My husband thinks it's stupid, but that's fine. He doesn't have to use it. So these are going to fill singly, and then they're going to pair up. And then, okay, so that's the third floor, but the 4S room is cheaper than this floor on the third floor. So the electrons are going to go up to this next floor. And then they'll start this one, because they're looking for the cheapest room, the lowest energy sublevel. They'll fill the beds separately. They'll fill the orbitals separately with parallel spins, all spin up before they fill and pair up. Okay? Any questions? So these are just some notes. Unless it's stated otherwise, and this goes in lecture, in worksheets, homework tests, unless it specifically says that it's an excited state, anytime we talk about electron configurations, we're referring to the ground state. So the electrons are all in the lowest energy orbitals that they can be. Let's remember that the number of electrons in a neutral atom is equal to its atomic number. So if we look at bromine on the periodic table, how many electrons does bromine have? What number is it? 35. That means it has 35 protons and 35 electrons. Okay? So the number of electrons for each element is just literally written on the wall for you. This is what we were talking earlier, how electrons with parallel spins, no, actually this is a little bit different. Electrons with parallel spins have a correlated motion that minimizes their mutual repulsion. So that's why they fill the separate orbitals with parallel spins instead of opposite spins. And then again, each orbital can hold a maximum of 2 electrons. And this reminds me of being in high school and college, and a club or a group or something would go somewhere and have to stay in a hotel, and right? And so you've got 4 guys in this room and 4 girls in that room, and there's 2 double beds in each room, right? And the girls would usually they would sleep together. It was okay. But the guys, you'd like arm wrestle or something and see who got the beds. And then one guy would sleep in the bathtub and the other guy just has to sleep on the floor, right? Well, you can't do this in this hotel because the floor is lava. Okay, so you have to sleep in a bed. Just get that out of the way. So when we talk about an electron configuration, it's just a listing of the sublevels in the order that they fill with the number of electrons in that sublevel written as a superscript. So this is like what the front desk clerk might have written down to keep track of what rooms are occupied. The 1S room has 2 people. 2S has 2 people. The 2P room has 6 people. 3S has 2, 3P has 6, 4S has 2, 3D has 10, because the D room has 5 beds. The D sublevel has 5 orbitals, 4P6. Okay? So that's what an electron configuration means. It tells us where the electrons are in all the orbitals. A shorthand way of writing that, because this is element 35, no wait, not 35, 36, and this is getting kind of long, right? You keep going and you just end up with this really long string, and the first part of this is all the same. So we have what's called an inner electron configuration or a noble gas configuration. And this is like a shorthand way, abbreviated way. So we're going to use the symbol of the previous noble gas in brackets to represent all of those inner electrons. So if we were going to write the electron configuration for rubidium, rubidium has 1 more electron than krypton, has 37 electrons. So we could write this whole thing out. But what's the difference between this one and this one up here? It's just this guy at the end, right? So instead of writing all of this mess, we say, well, the electron configuration for krypton plus 5s1.
Because 5s1 starts at 4.
Yeah, we'll get to that. Yeah, but it's always the previous noble gas. Well, why don't you just take these and put a thing and call that something, well, then there'd be like a ton of different abbreviations, and it would be hard to think about. And we like there to be one correct answer. That's something I really like about chemistry. Most of the time, there's one correct answer, right? There's not like multiple correct answers. Balancing a chemical equation, lowest whole number subscripts, right? One answer, not multiple. So here we're going to look at, we did hydrogen and helium. We're going to look at the next biggest elements, lithium, beryllium, boron, carbon. So you've got 3, 4, 5, 6 electrons, and now we have the orbital diagrams. And what I really like about the orbital diagrams is I think they look even more like a hotel. Because this is one room, and this is another room, you know, a bed in that room. And here, those 3 beds are all shown together, because they're all in the same room. They're in the same sublevel. And so as we increase the number of electrons, as the atoms get larger, we're just adding an electron to the previous one. And they're following that same pattern that I showed you when I was drawing on the energy diagram, right? So here, when we go from 5 electrons to 6, that 6th electron is going to go over here and take its own orbital, take its own bed, because it doesn't cost any more money, right? It's like riding public transportation. You get on the bus, and there's like some seats with people sitting in them, and then there's some empty seats. Do you go sit right next to a stranger? Not if you're a regular person. If you're weird, maybe, but everybody's going to know you're weird if you go sit next to a stranger. You should take your own seat if you can, right? Once all the seats are full, then if you sit down next to a stranger, it's okay, right? Same thing here. Okay, so let's write the orbital diagram for argon and see if we can figure out how many unpaired electrons it has. Well, the first thing we need to know is how many electrons does argon have? Argon is element 18, so it has 18 electrons. So argon has 18 electrons. So I'm going to sketch out the rooms in this hotel and the beds. So this would be the 1S room, and the 2S room, and the 2P room, and the 3S room, and the 3P room. And I know because I've done this before that that's far enough. So then we're going to put the electrons in here. And we're writing these in order of increasing energy or increasing cost to rent the room. So the first one's going to go in here. And the second one's going to pair up. So there's 2, and then 3, 4, 5, 6, 7. These guys are going to take their own bed because they can. And then 8, 9, 10, those are guys who are going to have to pair up. 11, 12, 13, 14, 15, 16, 17, 18. Think you can remember how to do that? Yeah. It's just electrons going to sleep in a hotel. It's really hard when I try to help somebody in grasp who hasn't been in my class, because I start talking about beds and they're like, what are you talking about? Okay, so this shows how all the electrons are arranged. Are there any electrons that are not paired up with another electron? No. So here's our energy diagram. Determine the number of electrons. Unpaired electrons, 0 unpaired electrons. And we'll learn in a little bit that whether we have paired electrons or unpaired electrons is going to make a difference in how these atoms interact with magnetic fields.